This video explains the paper titled, Implicit Steganography Beyond the Constraints of Modality. Steganography aims to conceal secret data within covered data in a way that keeps the existence of the hidden information undetectable. For example, when hospitals need to share patient information, it is crucial to hide it to prevent unauthorized access. However, as the amount of secret data increases, the cover data becomes more distorted, making it easier to detect the hidden information. This has been a significant limitation in traditional methods, which impose strict restrictions on the amount and format of the hidden data and increase the chances of detection. As a result, these methods face limitations in terms of capacity, distortion, and security. We considered the possibility of using implicit neural representation, in short, INR. INR is a new data representation method that moves away from traditional vector-based representation. Instead, it learns the data distribution through a neural network and represents the data using the network's parameters. In the case of an image, the input X would be the coordinates, and the output Y would be the corresponding RGB values. The neural network is trained using reconstruction laws to ensure that the output RGB values of the network match those of the image. Representing data through a neural network offers several benefits. It allows all data modalities to be represented in the same form, with only the input and output dimensions differing. Additionally, the network's size and depth can be flexibly adjusted. For instance, you can add extra layers or divide the network into multiple parts, with each part representing different data. This approach significantly improves capacity and distortion accuracy. Moreover, it becomes easier and more efficient to hide and encrypt data, thanks to the powerful representation capabilities of neural networks. A single network can be divided into two parts, each trained with weights from different secret INRs. When two parts are frozen and the remaining space is used to learn new data, the entire network represents the new covered data, effectively concealing the secret data. To further secure this, layer-wise permutation is applied, encrypting the position of the hidden data by permuting the order of nodes within each layer based on a private key. Instead of sending the secret data directly, the encrypted neural network parameters are transmitted. The recipient can then use the private key to reverse the node permutations and retrieve the hidden data from the network. Although we use the example of hiding two images within a single image, the modality of both the secret data and the cover data can be switched to anything else. In our paper, we propose the first framework that makes this kind of cross-modal steganography possible through comprehensive evaluation. We demonstrate that our framework outperforms existing methods in terms of distortion, security, and capacity. It is also more efficient and robust in real-world scenarios. Additionally, you have the flexibility to decide how many pieces of secret data to hide in the network and which parts of the network to use. These advantages make this approach applicable in a variety of use cases. For instance, an artist could hide their ownership information within their artwork or control the level of access to different viewers using different keys. In the sharing of data between hospitals or companies, this method could be used to embed multiple types of data, such as personal patient information or corporate secrets, within a single transmission. Lastly, it could be used by secret agents and security agencies to exchange confidential documents, disguising them as ordinary data to deceive potential hackers. The experiments consist of four main parts. First of all, in the cross-modal steganography experiment, we demonstrate that our model has the unique ability to hide multiple data across different modalities simultaneously. VoxLab consists of video and corresponding audio, while ImageNet is a well-known large-scale image dataset. In our experiment, we hide audio and video within an image. The figure on the right shows the covered data before and after hiding the secret data. It also displays the video and audio before hiding and after recovery. The key takeaway here is that our method introduces almost no noticeable distortion to the covered data, even with the secret data embedded inside. Additionally, there is minimal loss during the hiding and recovery process, making it virtually impossible to distinguish between the original and recovered versions. For the correct answers, please refer to the paper. In the case of the cross-modal steganography experiment, there were no direct comparison models, so a comparison was not possible. However, we conducted an intramodal steganography experiment, where multiple images were hidden within a single image. To compare our method with previous studies, the results show that our method significantly reduces distortion in both the cover and secret data. Since the cover data remains almost unchanged, the experiment also demonstrated that our approach offers superior security. Our model is highly efficient because it uses a simple MLP network to represent the data and employs straightforward methods for hiding and mixing the data. Compared to previous methods that directly modify the cover data for hiding, our model requires a much smaller network and, being self-supervised, avoids issues like domain adaptation. Additionally, to prove that our approach is practical in real-world scenarios, we conducted experiments on the degree of damage to the secret data in situations involving quantization and network pruning. The results showed that even after quantizing from float to int and then recovering, the secret data remained intact. In practical use, model size becomes important, so we conducted experiments to check whether model compression methods could be applied to INR. The left figure shows the PSNR and SIM values of the reconstructed cover data when fine-tuning at each step while gradually increasing the pruning ratio from 0.1% to 10%. As you can see, the data does not become completely damaged, and the values eventually saturate. Notably, the SIM values are well preserved, indicating that the structure within the image is maintained. The table on the right shows the results of an experiment where we increased the amount of secret data, while keeping the size of the cover INR fixed. Due to the efficiency and performance of INR's representation, even with more hidden data, it achieved high reconstruction results. This is a summary of our paper. For additional information and details, please refer to the full paper.